right. Any more? There's Lewis. 2 more. 2 more, come on. I know they can do it. No, 1 more. Miscounted. Yes. All right, well, we'll start there. Good morning, everybody. How are you all doing? I hope you had a wonderfully restful weekend, as I did, and you're back ready to get into the crack of things. This is where we're going to see everything we've been working on kind of all come clashing together, right? Solving those trigonometric equations using, well, at this point, we can use every trick in the book, which is why I had you on Friday write down every trick in your book for easy reference. Oh, good, Brianna's here too. Okay, we got everybody. All right, so let's take a look at this. Solving trigonometric equations. What to do with these guys. Some things to remember when you're working this stuff. And we'll go through a couple of examples together, and then I have a short quizzes for you that has a handful of conceptual questions and very simple, like very, very simple equations for you to solve on there. Okay, nothing like what we'll actually do in class or on your homework together. All right, so if you're trying to solve trig equations, I want you to remember first all of your techniques for solving linear equations and for solving quadratic equations will still apply. Those are still important. Those are still useful, okay? Especially when you consider good old, one bigger. The power of the U substitute, right? When you see something that says, oh, sine of x, you know, plus 3 equals 8, whatever, sine of x is one whole item, okay? If you think of that, use your u substitute, at least mentally, consider that this is just u, some other variable, plus 3 equals 8. This is now a very simple linear equation. You know how to solve it from here. Okay, solve it for u. Now go back and wait, u was that sine of x. Okay? You don't need to write it out this way every time, and we won't be doing that today, but that is one technique. If you're not seeing things right away, use that, simplify this, and to see what is happening to the trig element itself, peel the rest of it away in layers, and now focus lastly, okay, what about the trig equation? How do I solve that? Then you can go back and go, okay, now we inverse sine to solve for the rest. Okay. Now, with that said, when you get to the actual trig part, your reference angles and unit circle are going to be your best friends. Most of the time, these equations that you will be given are based on those angles. You're still dealing with 30s, 45, 60 degrees, 90 degrees, right? Pi over 3, pi over 6, pi over 4, pi over 2. Okay? You'll see those fractions or multiples thereof all the time. All of your unit circle angles will be there. And so knowing the reference angle, right? Reference angle being if here is my unit circle and I have an angle out here, I'm not looking at this whole angle all the way around from standard position. I'm looking for just this piece of it in order to help me solve, right? Okay. And final reminder, check the period of your function. Check the period of your function. The trick to trig equations, truly, because trig functions are periodic functions. They repeat over and over and over again. There is no single answer, not truly, right? And that's why they will often say, solve on the interval bracket 0, comma 2 pi parenthesis. And what the heck does that mean? Well, that means you're going to find all the values for x or theta or whatever your variable is between 0 and 2 pi. In this case, the notation tells us include the 0, but don't include the 2 pi, right? Difference between square bracket and round parenthesis, including 0, not 2 pi. That would make the equation true. Okay, the same old-fashioned definition of solve the equation from Algebra 1 is still important to remember here, because you break that down and you're not going to get confused by all the extra stuff. Okay? The fact that it's a periodic function. Use your graphing calculator to help you in this. Okay? It's a super powerful tool. It can't quite do everything, but is really great for getting an initial picture. Right? Graph the trig part that says, okay, sine of x plus cosine divided by tangent times cosecant or whatever it is, right? You're going to get some funky trig graph going there. And then all of that equals 5. Okay? So when you have sine of x equals 5, in your graphing calculator, you put in the first one, y equals sine of x. In the second one, y equals 5. So that will give you your trig function or whatever complicated combination of trig functions. And then 5 will give you the horizontal line. And now you can see, oh, look, every time they intersect, there's a solution, there's a solution, there's a solution, there's a solution, right? Every time they intersect is a solution. And now you just need to narrow it in. That's why they usually give you some kind of boundary, some interval there. Say, oh, just between here and here. Okay, well, it must be just these two then. Okay? That'll give you a visual picture of what you're looking for. If they don't give you that boundary, then you got to repeat yourself and be like, well, okay, the period, right? Sine of x repeats every 2 pi, so here to here is the same difference. So it's whatever this number is, right? This is your first x. To the second one, this is 2 pi. So it's going to be, the solution is plus any number of 2 pi, right? Plus 1 2 pi, plus 2 2 pi's, plus 3 2 pi's. And you can rearrange this. I've seen our text likes to write it as 2n pi, sticking the known integer, unset integer, and then pi, the transcendental. I usually do 2 pi n, just because I like to keep the 2 pi together, but it's all multiplication, right? It doesn't make a difference. But this represents your repeated solutions. The solution comes up again and again and again as it repeats itself, okay? All right, the other thing to use, your identities. Here's where all of them will start coming in handy, okay? Swapping between sines and cosines, right? Rewriting that tangent as sine over cosine. Maybe that'll be useful. Noticing, oh, 1 minus sine squared. Ooh, hey, Pythagorean identity. I can do something with that, right? Simplify, simplify, simplify. You are trying to solve an equation. You absolutely want the simplest possible equation. So use those trig identities as much as possible. But do be careful. I put it bright red for you. Watch out for extraneous solutions. Okay? When you use especially when you use the trig identities, you are changing, potentially changing the valid domains. Okay? The identities are equivalent, but they're not all of the identities are not always equivalent for every possible value, right? They have their limitations. Watch out for those domain limitations, okay? So you don't end up with extraneous solutions. So always double check your final solutions. Say, wait, does this actually work in my original equation? Okay. So there's the general advice. Any questions so far? Okay. Let's run through a few examples together then. So here's one. It says solve 5 sine x equals 3 sine x plus square root of 3. Man, why they gotta put that square root of 3 in there? That seems like it just screws up the whole thing, doesn't it? Oh, this is gonna get ugly. Maybe. But remember, sine x is one thing. I have 5 of a thing equals 3 of that thing plus something else, plus a little bit more, okay? Mentally, that's how I want you to read through and understand this. 5 things equals 3 of those things plus a little bit more. Okay? So with that in mind, all we need to do here, just subtract 3 sine x from both sides. Now you're left with 2 sine x equals square root of 3. Well, that helps. Now we only have the variable in one place. Okay? Now, continue to isolate the variable. Use your Algebra 1 basic equation solving skills. Divide both sides by 2. Okay, sine x equals root 3 over 2. Now is where we're down to just the trig function. Right? What values of x have their sign as root 3 over 2? Okay, so which angles on my unit circle have sine gives me the y-coordinate. Which ones have the y-coordinate? Square root 3 over 2. Okay. Well, in the first quadrant there, right, that would be this guy. Nope, that is x root 3 over 2 comma 1/2 for the 30-degree angle. Sine of 30 degrees is a half. So this is not it. This is the 60 degrees. Okay, or rather, in terms of pi, that would be pi over 3. Or you could keep going, right? Continue around that unit circle. So that's this one up here. We also have this one over here, which would be pi over 3, and then another pi over 3. 2 pi over 3 is the other one on your unit circle, and you could keep going. Right? Did it give me a bounds? Did it say find the solutions between here and here? No, it did not. I need infinite many solutions. So I need to keep going. Okay, 2 pi over 3, and we could just continue to list them. Or let's use that technique because we know the only ones on the unit circle are here and here. Don't confuse these guys down here, okay, because that would be a negative square root 3 over 2. We have a positive square root 3 over 2, not negative. So we're not using those ones. But you could, in theory, go from here all the way around and then stop, right? Or I could go all the way around twice and then stop. Any coterminal angle with pi over 3 will have a sine of square root 3 over 2. So we need to represent that somehow. So really, excuse me drawing, I need a little bit more room. we're going to scooch these over a bit. We need to be able to add some extra circles. Okay? So we're going to add 2 pi n to both of our answers. See if I can squeeze that in a little bit better. Okay. So anything that is 2 pi n more than pi over 3, right? Any multiples of 2 pi, so 4 pi, 6 pi, 8 pi plus pi over 3 will be an answer. Okay? And this is the simplest form that you can put in. That is our whole set of solutions. Okay, questions on that example? Anyone confused? How we got our initial answers, why we need to add 2 pi n? No? Okay. The next example here says solve tangent of 2x equals square root of 3. Oh, wait. They've got a limiter here. X is between 0 and 2 pi. Okay, so same as that wording before, right? On the interval 0 to 2 pi. Just different notation, right? X has to be between 0 and 2 pi. So this is going to limit ourselves. We don't need to add the plus 2 pi n's everywhere. We just need to find all of the ones that work in this region. So we will list them all explicitly. If there's 17 of them, we will list all 17. Okay? That's just what we got to do. So start off here, we've got tangent of 2x equals square root of 3. Treat 2x as 1 unit to start with, okay? So pretend this is, tangent of y equals square root of 3. Okay? Tangent of what equals square root of 3? Well, we could have, right, that y could be pi over 3. Right? And it could be right anywhere on your unit circle. Tangent, this is where it might get a little trickier here. So remember, a pi over 4 is going to be a tangent of 1 because x and y are equal, so that's no good. This is 3 over 2 comma 1/2. So your tangent, TOA, is opposite over adjacent. It's the y over the x, sine over cosine, 1/2 divided by square root 3 over 2, which is 1/2 times 2 over root 3. That's 1 over root 3. If you were to rationalize the denominator, you multiply by root 3, and you get 3 over 3. Okay? Now up here, pi over 3, we have the reverse, right? We swap these, so we can switch those. So instead of 1 over root 3, it's root 3 over 1. Okay? So use that knowledge of your unit circle, build up that foundation until you get to the point where you can recognize this. Oh, it should be pi over 3. So instead of y, right, that's really our 2x. Treat it all as one thing. So 2x equals pi over 3. Okay? And that's anywhere that is similar, right? The period of tangent is not 2 pi, it's 1 pi. Okay? So this is, in theory, plus any multiple, integer multiple of pi. Okay. So that could be 0, 1, 2, 3, so long as they fit inside this interval. Well, that's the interval for x. So let's go ahead and divide by 2. Right? We want a single x. So divide both sides by 2. 2x equals all that. X equals, okay, pi over 3 divided by 2 is now pi over 6. Plus n pi over 2. Right? Divide the whole thing. So far. So now we got to find all the solutions that fit in that interval. Okay? So I'll start with the lowest, right? The smallest possible. Set n equal to 0. Well, then we have x just equals pi over 6, right? Pretty straightforward. How about if n equals 1? 1 lap around tangent, which we should expect that to land, right? If all students take calculus, all the trig functions are positive in quadrant 1, sine is positive in quadrant 2, tangent is positive in quadrant 3, and cosine positive in quadrant 4. I expect tangent to give me something, right? Tangent will give another positive value. I expect at least one more. Although this is 2x, right? We've stretched it, okay? Think about what that means. I've multiplied the x's here. I've stretched it, actually shrunk it, right? This is a horizontal transformation because it's happening to the x, and it does the opposite. Multiplying by a number greater than 1 usually makes things bigger. It would stretch it out, but it's inside, it gets reversed, it's shrunken it. So I'd expect actually there to be more than 1 in here. Right? Use that background knowledge to set your expectations. So we're going to get x equals pi over 6 plus 1 instance of pi over 2. All right, pi over 2 is, of course, 3/6, right? 3/6. So plus another 6 is 4/6. So that's 4 pi over 6, which we can actually reduce 2 pi over 3. So there's one solution. There's another solution. Keep going. What about n equals 2, right? This is still less than 2 pi. In fact, it's less than 1 pi. I would almost expect the fact that I got 2 answers between 0 and 1 pi leads me to think there's probably 2 more, right? In the between 1 pi and 2 pi. So let's get those real quick. Pi over 6 plus 2 pi over 2, right? It was 1 pi over 2. Now we have 2 pi's over 2, which is just pi. So pi over 6, now that gives us full pi plus an extra 6 would be 7 pi's over 6. There's a valid answer. Okay, how about for 3? Pi over 6 plus 3 pi's over 2. How many 6's is that? That would be 9 6's. Plus another one, 10 6's. Reduce that. 5 pi over, no, 3. Okay. Can we fit one more? Let's try. What if n equals 4? We would have pi over 6 plus 4 pi over 2. Oh, wait. 4 pi over 2 is 2 pi. So that would automatically be greater than 2 pi. Right? So nix that. This is our last solution. So you just set all of those together, our x's could be pi over 6, 2 pi over 3, 7 pi over 6, and 5 pi over 3. At that point, I've got 4 good points there. I can kind of see the pattern here, right? 6, 3, 6, 3. The next answer would be 6's. We had 1, 7, right? 7, 5. So 3, 5, 7. Right, you could kind of continue the pattern there even without adding by hand if they wanted more of them. Questions on that example? No? All right, last one. Solve sine x tangent x equals sine x on the interval x is between 0 and 2 pi. Okay, that looks really common. Let me add one extra detail here. This is just sloppiness on the part of the textbook. I don't know why they do this. Right? Please put parentheses around your function arguments so I know that this is sine of x times the tangent of x and not sine of x times tangent x, right? I know that one function is not inside the other. Make it absolutely not ambiguous. All right, but this is what we're dealing with here. Now we got to multiply. Well, sine times tangent. Well, tangent is sine over cosine, and so that would be like sine squared over cosine equals sine. No. This is more complicated. You can use that, and maybe if it simplified things, sure, you can use that rule. But in this instance, I would actually move the sign to the other side. Minus sine x equals 0. Why is this helpful? Might not seem obvious. But this is the old algebra standby that is going to carry you through, especially in calculus. When in doubt, factor it out, right? Because now I can factor out the sine x, okay? Why am I going still in green? Back to blue here, right? Factor sine x, right? Divide this by sine x, we get tan x. Divide this by sine x, we get minus 1. And that doesn't look much better at first, till you remember, right? What did I say at the beginning? Use your linear and quadratic techniques. Beautiful, beautiful quadratic techniques, right? Quadratics is where we really started getting into the factoring. It still applies here. Because after factoring, you can now apply that most wonderful of properties, the ZPP, zero product property rule, that says each factor, if multiplied, gives 0, then either this factor equals 0 and or this factor equals 0. So now I can make two mini equations, right? I can split this apart. I know either sine x equals 0 or tan x minus 1 equals 0. Now those are very manageable, right? Sine of what angles equals 0? Okay, on my unit circle, sine is the y value. Where's the y value equal to 0? That would be, well, that would be 0 right there, clearly. And all the way around, full turn there, pi, right? Or if you want to think graphically, where does the sine function cross the x-axis? 0, pi, and 2 pi, but wait. Or equal to 0, but no or equal to 2 pi. So we stop just shy of 2 pi. We do not include the 2 pi. So on this side, we are stopping here at 0 and pi. How about over here? We can add 1 to both sides. Tangent of x equals 1. Where does the tangent equal 1? Remember, tangent is the y over x. Okay? What angles on my unit circle, right, are perfectly symmetric that the x value and the y value are the same? Right? Y over x equals 1. That would be my 45s, or the pi over 4s. So x equals pi over 4. X equals, what about here? No, that's got to stay positive, positive 1. So it's going to be down there in the third quadrant. So 1, 2, 3, 4, 5. 5 pi's over 4 is my other one. Right. So then we got to combine all 4 of these. Our final answer for the original equation is the full set of 0. Let's try to put them in order. Pi over 4, pi, and 5 pi over 4. Okay? Questions there? No. All right, then let's make sure I've got the right settings on here. Live quiz, 1 answer. Show the answers. Yep. All right, then let's get ready for a quiz. Quizzes. Go to joinmyquiz.com. Enter the game code 669169. And again, these the questions here are much simpler. They are not as complex as the examples we've just done. They are just real simple, more conceptual in nature, so you will not have to calculate them out quite as lengthy there. Your homework problems, those will be like the examples we did. Okay. All right, I've got 3 in. Four, 5, halfway there. All right, as always, a retake link will be posted at the end of classes today. It'll be open all week, in fact, indefinitely, as all quiz retakes are. You can continue to retake them. Remember, this is the last week of the quarter. This is the last quizzes of the quarter. So if you want this grade to appear in your quarter report, then you definitely have to get the retake done by the end of the week. That would be Saturday. If you have any other quiz is to retake, please be sure to email me to let me know that I need to update those scores. All right, but with that, we will stop the